going to give us the last lecture of this year. I think it directly touches on maybe hopefully exercise, okay, obliquely or directly touches on exercise 4 and 5. So, okay, sorry, when you're ready.
Okay, I'll start. So I think from exercise 1 to 5, at least the way we're looking at all these exercises as formal languages and syntax. So what are formal languages and syntax, right? It's basically if you're a writer, then you're looking at the whole essay or novel structure, and then you have vocab or grammar or things like that, right? Or if you're a musician, basically you have a musical score, and then you have notations and to describe a piece of music. So when we are looking at past projects in history, right, we are looking at the formal languages and that architects use to design or generate forms, right? So there are a lot of ways to look at projects from history, but like styles, like political significance or social significance, right? But in this lecture, I'm going to focus on just formal languages, right? So how do you make forms, right? So the first period is the classical period. I call it primitives to describe the geometry, right? So this is roughly belonging to the classical period. So I'm not going by time, right? And the languages we have is like symmetry, primitive. Sorry, I'm very distracted by the studio next door. Sophia can help me. They are making a lot of noise. Yeah, okay. Okay, so the first era or the first set of languages, we are looking at basic geometry like circle, square, rectangle, right? And then we are looking at things that's like symmetrical. You have axes, intersections, and things like that. And then the way they go from 2D to 3D is by extrusion, right? So you have seen these models by Moretti where he tries to build solids of the voids, right? So in section, sometimes it's a circle and most of the time it's extrusion. This has to do with the material, which is brick, during that time where they stack all these bricks up together. And then we have Corbusier looking back at all the Greek and Roman architecture and then making a drawing of all the Platonic solids, right? So you have cylinder, pyramids, cubes, and things like that. Okay, so this is a quick summary of the language of the classical period or language that's invented during the classical period, right? So circle, triangle, square, and then you have extrusion. So you can easily describe the circle by a radius and a center, or the rectangle by the length of the sides, right? And then we go to the second set of language, the Cartesian language. So this is invented during the Modernist era. And then you have ideas like 4 square grid and 9 square grid. So basically talking about there's only 2 types of grids, right? So 4 square grid meaning you have a column in the middle, and then 9 square grid meaning you have a space or a void in the middle. So most of the classical buildings, they belong to the 9 square grid because they are religious buildings and you have to walk down the aisle, right? So a lot of the buildings created in Modernist era, they try to do 4 square grid, right? Just as a discussion. Or so you have here Villa Savoie. It's a classical 4 square grid, and then so in the middle, instead of a column, we have a ramp, which is also a space, right? So there's all this discussion or modification, right, of grid. Villa Stein, of course, and then it's a classical AB grid, and then by shifting the entrance to the side, you start to generate diagonals in the architecture, right? So this is the classical, this is the classic domino house diagram where it shows you the pilotis, they are either placed on 9 square or 4 square grid, and then these are then stacked, right? So instead of extrusion, you now have floor by floor stack up, right, to make into 3-dimensional. And then the grids is a structure system, but then in order to demarcate the spatial experience, you have all these walls where you call what's called infill walls, right? So they are usually curves, and they are kind of like shifted or deflected away from the grid itself, right? So when you're inside, you don't actually experience the box or the grid, but you experience all these curves and all these spatial elements, right? So you have Mies, who has all these points, lines, planes sliding along the grid. It's never really on the grid, right? So you generate a lot of dynamism, right? And then you have John Hadid, where there's a lot of rotation between the frame and the object itself, right? So again, you see a lot of use of all these curves, right? So in summary, we go from basic geometry extrusion to modernist, where you have a Cartesian grid, 4 square or 9 square, and then the circle is now broken down into arcs, right? And then all the triangle is broken down into planes, which are rotated or slide away or along the grid, right? And then to make this form in 3D, all these are stacked, right? And every floor is different when you stack. Okay, so now we go to parametric form, which is essentially exercise 4, at least in meditation, right? So parametric form looks something like that, right? It started with Gehry making the fish, and this is his Bilbao museum built in 1997. Or buildings like SANAA Hadid, right? It looks like that, right? It's like, oh, parametric, right? Or at least the image of parametric form. So this is how Gehry start designing, right? So you take a piece of cloth or a piece of paper, more cloth, and then you crumple it, right? So, and then this becomes a building. So you can look at, so what is this? So this piece of crumpled material is very difficult to build or describe geometrically because it's not a circle or a square that you can set out easily, right? It's also not points, lines, planes. There's also no grids, right? So if you look at a fantastic lecture by Mario Capo, it's called The Second Digital Turn, right? He described this era of architecture as the first digital revolution, right? So he's talking about potato. So he said the form that Gehry or Zaha made, right, this crumpled piece of paper is a bit like a potato, right? So it's very hard to model this potato in software or describe it geometrically because it's not really a circle, it's not really a perfect sphere, right? So we have to come up with ways, right, to describe this complex geometry, right? So one of the ways this is done by Sutin this year, my studio, right? So the way they have an exercise, thinking of ways to describe this potato, right? So you take a piece of potato and then the easiest way is to chop them up into slices, right? Then you trace all these slices, right? And then you loft them together, right? So by chopping anything complex into slices, a lot of sections, right? So this is CT scan of a foot, right? Your foot is quite complex to model geometrically as well. So by having a lot of sections and then connecting these sections, you somehow can easily describe any complex form, right? So this is the potato. So the function that you can do in Rhino is called contour, right? So you have X sections and they are all X distance apart. And then you can take two curves and you do a lofting, right? Lofting basically means you connect point 1 on curve 1 to point 1 of curve 2, and then you just join the points together and you form a surface, right? So you can see a lot of, this is another one of Gehry's model, right? So you can see here he's using contour, it's just equal distance, chop up the whole building, right? This is from the form actually is from a piece of crumpled paper, right? So he realized it this way. You can see, right, different sections going through, right? So this is one way. So or Zaha Hadid's Galaxy Soul whole, right? So it's the same thing. It's like a smooth amorphous shape, and then you just have infinite sections, right? So there's another thing that you can do. So when you describe all this complex geometry, you don't always have to chop up the complex form in equal section, right? So there's this idea of critical sections, right? So you can maybe just describe a few special sections, for example, the belly here, and then the peak here, right? And then you do the lofting. And after that, you can then rebuild them into surfaces with equal division, right? So something like that, right? So let's say now you have a peanut or a weird shaped potato, right? So instead of cutting many slices, I can actually just describe the shape by the extreme sections, right? And then I can connect them using lofting, and then I can rebuild this UVW mesh, right? So no longer we don't use XYZ anymore because this is subdivision along the curve, right, or the surface, right? So another example, so this is the fish that Gehry was trying to build that kickstarted this whole era, right? So this, like, how do you build this shape, right? So he basically, these are the critical sections, right? That I don't know where you can see my pointer, right? So they don't even have to be planar. They can be just curved in space, three-dimensional curves, right? And then you can do a lofting, right? So these are the basic sections that describe the geometry of fish. And then when we rebuild the wire mesh in he's using Cartesian, but you can do it in Rhino, right? So you start to get equal section, and that becomes the structure of the fish and also the structure of the cladding, right? So you can see from the paper that you saw just now, like now you start to see the structure behind, right? That is whether it's equal or unequal. These are done using the UVW mapping, right? So in Zaha's project as well, so you can see sections and sections of steel structure, right? The way you so the sections are of course the same, like Kobu's pilotis, right? Yeah, most of the time the same, the span, or you have ABE, but in this case, every section is different, right? And most of the time, this is Gehry's facade, right? So you subdivide in between the structure, and you get the substructure for the cladding, right? So Rhino, right? So this is a rebuilt UVW mesh of Rhino, and then you can, it's a very complex form, but you can see how every panel they have along this curve, right? You can see how every panel they have equal distance now, right? So this is a technique that is developed during this era, right? So we recap, you have this cloth as a starting kind of thing, but you can't really build your building with a bigger piece of cloth in real life, right? So you have to make them into something like panels, right? So this is a better, more detailed model where you start to make it into strips, or in this case, you can see, right, you start to get panels, right? So this is what they see. Again, you see the UVW mesh being the panels, right? So in real life, when you build, this is what you get, right? So all this UVW becoming the panel of the building. And just now we talk about structure, and this is the outside, the surface or the cladding of the building, right? So a lot of Zaha's building, you can have this kind of trapezoidal panel, which is from the UVW mesh, right? So smooth, something very smooth, to something that is trapezoidal. Then you can also further make it into some triangular panel, right? So this is a rabbit, and you can make it into different resolution of triangle. Or if you are more advanced using grasshopper and things like that, you can make them into hexagonal or any shapes you want, right? So these are called the technique of paneling, right? So Joel this year also did the paneling, like a Volmer paneling for potato, right? So you can build potato that way. So you have more complex surfaces. Okay, so recap. So some of the techniques of this era, right? You have a smooth surface, and you can do contour, then you can get a UVW wire mesh, which then becomes your structure and your panel division, right? Or you can do a triangular mesh, okay? So again, this is the fish, right? So you see the form that is, that's how he started. He took a piece of wood and then you carve the fish. But then to build it in real life, you actually have to break them down into smaller mass customized elements, right? So you have the contour forming the structure, and then you can have all this paneling, which is the cladding, okay? So at the end of this 2000-ish projects, right, there are some problems, right, with this way of doing architecture, right? So one of them is they look like parametric form, but if you look at the inside, right, you get a lot of subdivision of the inside spaces. So they are just forms that it looks nice when you look from outside. And if we look at the sections, you can see that the sections are still stacked, right? So all this parametricism, they are kind of like applied to just the cladding itself, right? So the inside of the building is still no difference from a domino house, right? Which is stacked, right? So this is the problem that they realized maybe early 2000, right? So I think exercise 4, yeah, so when we do a lot of this kind of form, so you can see here, this is a triangular mesh, right? But when we want to translate or be more specific, like the question is, how do we avoid doing extrusion, or we avoid doing stacking, which is from the modernist and the classical era, right? So we have here Gehry, like, this is him like doing a stage set with really just crumpling any paper, right? Then so the question is, can we use data to justify some of this deformation or this form making, right? Rather than I crush this piece of paper I like, and can we be more specific when we have like all this endless I don't know, clay or anything? Because now with this, what is the difference between this version and the top version, right? How do I choose? How do I control all these points, right? So can this data help us, right? And how do we go from something very smooth, right? On the left, you have all this smooth material, and then, but to build it, we always have to make it into discrete objects, right? So that's a challenge. And then going into the second digital age, right? So recap here, you have classical, modernist, and parametricism, right? Where you have free-form curves or like odd shape, deformed triangle, deformed rectangle, and then you do lofting, right? And then contour and things like that, right? Then we go into the second digital age. I think we are currently still in the middle of the second digital age. So this is really just my reading of it. I don't know, different people have different reading, right? But what I'm looking at is series, like the idea of a topological series, right? So just backtrack a little bit. Now we go to Japan and look at some Japanese architect, right? So Ito built this in the year 2000. This is a Sendai MediaTek, right? So it looks like this, and these are the columns of space going through the building, right? So what he was trying to do, he was really reacting or trying to critique this domino house diagram, right? And then now he's like saying, oh, can I have not pilates, which is solid that I cannot enter, but actually I can have a few of irregular pilates, right? They are not straight up, they are also spaces. So if you see here, some are spaces, some are staircases, some are lift or rooms, right? And then they start to stagger, right, from floor to floor, right? And then on plan, they are also kind of like scattered, right? They don't sit on the 4 square or 9 square grid, right? So you have a few of condition from very small columns to big columns, which are also spaces, right? So then you basically have a family of columns, right? So, and then there's this idea of topology, right? So basically it's saying in the mathematics of topology, the donut and the coffee cup, they belong to the same mathematical family, right? So they are basically, sorry, here donut has a hole, and then if you imagine this as a lump of clay and you morph them off, eventually it will become a coffee cup without actually cutting, right? So there's this idea that these objects, they look completely different, but they belong to the same mathematical family, right? So you have a series of things like that, right? So it's about relations, new ways that you can describe geometry, not just how it looks like, okay? So we are going into topological series, right? And then looking at how, instead of one triangle or one deformed triangle, we are looking at a family of triangle of different shapes and sizes. And this is what Grasshopper allows you to do. So you can define variables, right? So if I define variables of the triangle being the base times the height, and then I can vary the base length and the height, right? And then I'll get a family of all this triangle, right? Or if I just vary the circle, the radius of the circle, I'll get this whole family and series of circle and squares, okay? So this idea, and why are we doing that? Because we are going towards something that is mass customization, right? Rather than mass production, right? So you're like trying to make a series of, or a family of potato, not just one potato, right? So what variable connects all this potato together, right? So can we have a series of forms, right? And then which then you can apply whatever your selection criteria is, right? And then they look different, but actually they are from the same mathematical series, right? So this idea of series. Then we look at some buildings by SANAA, right? So this is 21st century museum, right? So you see just simple boxes, but actually this is a museum. So every gallery or box is actually different, right? So they're trying to actually make a family of boxes. So instead of like room after room that is the same, maybe in this museum we have one whole spectrum of spaces, right? So whichever, so you provide all the exhibition content, right, with a range of spatial experience rather than the same thing, right? So in this way, maybe architecture can be more like nature and can be more interesting instead of having repeated things, homogeneous things throughout, okay? So this is, they also made a house, a Moyama house. So this is supposed to be 10 apartments, but they are making every space a little bit different, and you try to have, again, 10 units of different spatial experience rather than the same thing repeated, okay? And then you have Ito's museum, right? So trying to create, again, a family of folds, right? Three-dimensional folds, and then you put together so that you get whole series of different folds which will give you different spatial experience, right? So architecture has moved from industrial era to this era where you can have mass customization, right? And computer allow us to do that very easily. Okay, so some of the artists, I think Yen also talked about this, right? So Louis, right? So basically you have a equation or algorithm, but then the artwork, because of the variables that's different, then you will generate a series of artwork that is different, right? Or you made sculptures like that where there's variations of open cubes, right? Just the first series is just any 3 connected sides, right? So you get this whole series of sculpture, and then the last one is maybe 6 connected sides, right? So, or you have Eva hairs, right? So just using the property of ink, and you try to create variants and individual family of things, right? So the best, the best example is probably Kite, built by Ishigami in 2008, right? So these are columns. Then we look at clustering of columns, right? So instead of grids or a certain shape, right, we suddenly have things like density of columns, right? So this is a student center for university in Tokyo. So basically, it's like going to a forest, right? If you feel like hanging out in a place where there's more privacy, maybe you go to somewhere here where the columns are closer together, right? Or if you need to do something that needs more space, then maybe you will do that, right? So they are not functional specific or program specific, but they describe a range of spatial experience, right? So whatever you want to do, right? So if you feel like you want more shade, then you go to the dense area. Okay, so these are the series of columns with different rotations that he can generate. So he describes this building differently every time. Sometimes he said, "Oh, these people hang out. This is like birds flocking or swarming, right?" So you look at different density, or sometimes they are further apart, right? Or sometimes he say, "Oh, maybe it's like galaxy, stars, or it's like trees, like forests, right?" And then the crown of the tree versus a tree trunk. But in general, it doesn't matter what he says, right? But if we just look at the form, you have the property of the density, right? So you're defining boundaries, not like by a wall, but by a dense spacing of columns and things like that. Okay, so you have a few conditions with a spectrum of spatial experience, right? So from outside, it looks pretty much very clean, right? So it's the total reverse of the first digital era, where from outside it looks very complex geometrically, but when you enter, it's actually just a domino house, right? But here, from the outside, you just see all this equal division of glass, right? But then you spend a lot of time inside because the structure inside or the spatial organization inside is very complex. Okay, so the Japanese architect sometimes talks about the being in the inside of the building, the continuation of the inside of the building to the outside, right? So they want to actually blur the boundary between architecture and the nature, right? So now architecture is more like moving towards nature, right? So if nature has the whole spectrum of like infinite spectrum, which means every tree is different, right? So maybe SANAA, Nishizawa, all this, they are trying to achieve maybe 50 variations, whereas compared to the modernist or the mass production era, you are looking at ABA, 2 or 3 types, right? So maybe SANAA's architecture or Ishigami's architecture is somewhere in between that, but it's closer to nature, but it's still not yet nature, right? So theoretically, you can look at Deleuze 1002, right? So as an idea, right, he describes nomadic society versus sedentary society, right? So basically, centralized system versus decentralized or distributed system, right? So centralized is like hierarchical, is top down, it's like a tree system, right? You have a tree trunk and then go into branches, and then whereas the decentralized system is something like rhizome roots, right? So you can cut any part of these nodes and then they can just grow, right? So it's non-hierarchical. And if you want, this is like organization chart, very typical, right? Versus some sort of flat hierarchy, right? So from there, I think, I don't know, to me, this is the core of exercise 5. Then we don't just stop at rhizome, but we are looking at what other systems, right, that we can think of, we can find in order to generate form that is not a tree system, right? So even without Grasshopper, like conceptually, you have to understand this is, maybe this can be related to material, okay? So like if I have this sculpture, right, where actually the mold is the same, but because of the nature of this rubber material, right, when she took out the mold, then every one of them, they look slightly different, right? So this idea of maybe using materials to also find form, right? Dynamic models. This is a model by Gaudi, right? So for this building, this is Sagrada Familia. Basically, Gaudi back in the 1800s didn't have grasshopper or rhino. So he used chains and weights, right? This is the arches upside down, right? So he hang all these weights and try to then find the arches and the form of these arches for the whole building, right? So this is a good way where you use physical modeling, dynamic modeling, right, to find form. And then he also built this chain model for another building. Okay. And then the other architect that we can look at is Frei Otto, right? So Frei Otto did, you see this building is this model is also upside down. So it's trying to use bubble actually to find the form for a tent-like structure, right? So he hangs all this thing upside down, and then he used like bubble in different ways, right? And this is eventually the tent structure that is built, right? So something like that. Then of course now you can easily do that with kangaroo in grasshopper, right? But back then when they didn't have all this digital software, is using models like that, right? So if you are interested, you can look at this book, right? This book has a lot of experiments or model that he has designed to find form without grasshopper. Okay, so this is something like this is to study distribution, yeah, right? Or bubble in another way, right? Different sizes of bubble, and then how do I control the clustering or the flocking of the bubbles, right? Or like to study Voronoi organization, right? So you can see he did, and then he tried to do all this diagram, right? And then now we can just, with very simple script, you can just do a Voronoi structure, okay? And this is studying flocking, right? So again, still using bubble, but here he controls the sizes of the bubble, right? They're all the same size, and then he's just studying how they cluster together, right? Or using magnetic fields and how all this flocking happens, right? So, or something like that, right? This again, you can use attractors or other plugins, right, in Grasshopper to study now, okay? Yeah, so I think exercise 5, maybe can focus on the finding of all these relations, right? So instead of the form itself, right, but how can we get a few variables that we can model in Grasshopper, and then eventually use that as an organization structure for the building, right, rather than the form itself. All right, so this is by my student last year, where she was trying to study the sand and obstacle, right? So different gaps between the obstacle and then different sand grain sizes, and then she's trying to study sedimentation and some of the deflection, right, of the bounce of the particles, right? So this one, right? So you can and then what does this mean in architectural project, right? So this is not the form itself, right? But you can say, I don't know, the bounds can be applied in different ways in different building, right? But basically, this kind of bounds relation is very different from, let's say, grids or some other systems, okay? Then you have Jerome. So the exercise last year was a bit different. I think this is for the notation exercise. So he was basically trying to study the fish swarming together, right? So different numbers of fish and how big they are, and you'll create this whole relations between the fish, the size, and da da da. So you get a series of relations. Okay. So of course you have to need more time to translate this into form. Yeah, I think that's it then.
Oh, well, I have questions. As always, but any student or tutor who wants to chip in or comment about how they intend to approach exercise 5 vis-a-vis what Sai has shared can also do so lah.
Yeah.
I have a question about the Frei Otto one. Because Frei Otto's the kind of bubbles, exercises, surface tension, Voronoi sequence, it's obviously based on bubbles lah, right, which has a certain materiality. So when he then translates it into catenary structures, which are obviously not made of bubble nor water, there is still some sort of an assignment of affinity to material, right? Like at least an affinity to performance, although I would say bubbles don't really work the same as stretch catenary structures lah. There is still some form of it's not scientifically one-to-one mapping. One is a volumetric, one is a volumetric kind of inside blowing up, and then the other one is kind of like stretched. So there is also kind of like a translation. Right?
Yeah. So basically, I mean, he used bubble for everything basically, but it's how you control the bubble, right? So in the beginning, it's more like the whole surface, right? He's trying to find that, and then after that you have the Voronoi one, then you have the clustering one. At least 3 I can understand, right? But they're all bubbles, right? And then if you want the first one, you can also don't use bubble, right? Like when you go to kangaroo, actually you can go into fabric, like tensile material. You see? So yes, there's a relationship, but it's not one-to-one.
Yeah, so we need to find the most affinity of relationships, because in Frei Otto's example, he can start with bubbles, but he could have ended up with another material that is not a stretchy material, for example. It could not have been a tensile structure. It depends on what he feels is most translatable in the performance.
Yeah. So it's like this, you basically use this to find a series of forms, right? Then after that, eventually you have to choose one to build, right? So when you choose one to build, then you go back to exercise for the, you can describe it with unlimited sections, you can do paneling and do structure and all these things. But this
had he not gone with tensile structures, let's say he went with tensegrity, which is just, not catenary, right? Is that possible? It's not, right? Because it's different performance.
Tensegrity is a system itself. So it's, but let's say I can take this, right? For example, this form, but then I don't want to use a fabric or tensile structure, right? Yeah. I can build it with rigid materials, right?
Yes.
And I can also do that.
Let's say a series of springs, right? Let's say a series of springs. He uses a series of springs that will just self-organize, self-adjust until they find this perfect optimal shape. So he does need to also make that decision of assignment. I say assignment. Yeah. What is the most likely buildable material he can use to translate this performance, right?
Yeah, that's right.
Then between exercise 4 and 5, obviously 5, it's completely almost performance driven. It almost like in kite workshop, it doesn't even matter whether it's a round column or a square column or it's a column at all. It is the kind of resultant space in between that prescribes what the characteristic of this performance is like, rather than it's almost like the negative of the columns that makes that, right? So in a way, also in design, we have to find what this object to populate this field in exercise 5 is going to be, right? It can be, like I said, it can be a round column, it can be a beam, it can be any of those things, as long as we take it as a particle unit and then we push it through the exercise 5.
Yeah. You can, it's more the system. Is it you see, he found, maybe the human, the birds, the stars, the trees, right? They are kind of the same if I'm just talking about density and flocking. You see? So it doesn't matter even what, but it's like that's the character of the room. Yeah. But I can also I can also use another shape, right? But it's the idea that you have this spatial structure that's based on density, right? Or porosity, some less dense, right? And then you have a new structure system for the building rather than just applying parametricism to the cladding and the facade itself.
Right, but this flocking system of his, the KRIT one, structurally, it might not be the most efficient either because,
Yeah, it's not.
right, it's completely not because it is almost focusing on the parametric space rather than the structural integrity, the most efficient
Efficient will be
structure.
domino house, right? That's the most efficient already, right? If I want to be efficient, I'll do this. This is nothing.
Correct. So I feel like there is this jump from what is exercise for finding the most optimal, rational, buildable form in free form, in complex structures, rationalizing it into a Gehry fish that's buildable, and then kind of going completely the other way with kite, which is focusing on parametric space, and maybe the way you cluster columns is completely not even generatively the most efficient, you know what I'm saying?
Yeah.
So
But this
is a
But
different.
this is also, I don't know, for me, this is also not very efficient. But then, like, you do a lot more, but then when you enter the building, it's still quite predictable, you see.
Yes. I'm not suggesting
Like,
we should do Zaha's building, but I'm suggesting that maybe kite is also not quite progressively the next step from exercise 4. Maybe Frei Otto would have been progressively, strangely or futuristically, Frei Otto would have been a more natural progression from exercise 4 to 5.
that's why, I mean, like, now is not the most efficient, but that's why they are hoping to print a building, right? If I can print a building, I don't need to rely on traditional industry to fabricate. Then kite becomes efficient. It's easy to build, right?
But kite would never be efficient.
Why not?
Hey,
If I'm printing the whole building.
Hi, Bo. Can you hear me?
Yes.
I can't see myself because I'm driving to school. I think the conversation is great because you talk about 4 and 5. I think Frei Otto is more like exercise 4 because it is really based on film, right? It's a form, it's structural finding of a form. So it's 1-for-1, almost 1-for-1 mapping of that form to get the best surface tension, right? So if you're
it's about, it's not one instance. So I think you have to.
Yeah, I know, I understand. Yeah, I understand it's not one instance. There are multiple instances of this. So what I'm saying is that I could, because it is of I mean Frei Otto for Frei Otto's sake, and his work, right? Through the work that he is trying to do is actually to get a parabolic, right, surfaces, right, and forms that he wanted that. And the only way to do that in those days is really to work with an experiment, right, with soap, right, and to test multiple different optimization, right, to get the different form out of the soap film, what soap film can do for him, right? So I think if that's the case, right, the multiple different possibilities of what soap film can yield him becomes his structural formation, you see, right? So it isn't, then wouldn't that, I mean, that I can really relate back to this. Well, I agree that it is topological in the sense that because there are multitudes of these possibilities, right? In that sense, sorry, maybe I should rephrase myself. It shouldn't be an exercise 4, but rather it's an exercise 5 idea.
Yeah.
Right?
I agree with you there, right?
Yeah. So in terms of efficiency, right? If you look at the propagating of columns in kite, really the idea of kite is the idea behind that that structurally arranged spaces, right, in a different syntax, in a totally different syntax. So it's an algorithmic relationship, right, that generates this series, of dense and dispersed, right, space, right, as a result, of the idea, really, behind the idea of kite. So if you are saying that it's not whether it's propagating, you can, I think it's not a matter of whether it's propagating a round column, fin, or a square column, or a cross column for that matter, right? It is the structure itself is that space in between that forms the relationship from the densest to the sparsest. Right?
Yeah, but I mean, but they are
yeah.
looking towards the end goal is quite different, right? Like if exercise 4, you see that the people are moving towards rationalizing potatoes, rationalizing all that.
No, that's correct.
I
that's
don't
correct.
see the new, I don't see kite specifically as something that helps to rationalize structure the way that he's clustering it.
I think
in
that
a
is,
very
I mean,
orthogonal form, in a very orthogonal form does not require that
not.
operation at all, right?
Yeah, it's not. You're right.
No,
Yeah.
actually, sorry, no. Because exercise 4, like, there's no rationale. He just crumpled a piece of paper. Like, I want to build this form. So when you want to build anything, you will go into the rationalization. But the design process, right, is like that lah, right? Then what we're trying to do is we try to use data to justify this crumpling, right? So exercise 5, eventually when you want to build it, you will still go into this kind of rationalization. But I'm saying whether the design process, right, or this data, you use relations, right? You look at flocking, you look at density and things like that. So that is the design process that is very different from I just want to convert this, something like that. So you are actually applying the parametricism to the design process rather than just the
but I feel like there is a bit of disjuncture that like Julian Ishigami is not really following from that school,
I mean he doesn't code,
and I struggle to find an example that would follow from that school of that the kind of more kind of linear rational kind of evolution of, okay, so I'm done with exercise 4, actually the right thing to do is how do we do optioneering, how do we do generative that also helps with complex form, also rationalizes structure, but also based on the performance. For example, Akim Minger's work, right, is about rationalizing forms structurally, in order to understand the performance of distribution of weight or load, for example, right? That has a more kind of direct translation or more direct application.
But actually, like after you do this flocking and you have the series, right, you can actually run through like Galapagos or some of these things, right, to actually select those that's more structurally optimal.
Yeah.
You see?
Yeah.
So you can still do that. But I think the crucial step is to apply this parametricism thinking to the design stage and the structure.
Okay, yep. So I feel like exercise 4 and 5 should be seen as completely different lessons, unless we're so good at finding that one method or one kind of like synergistic way of making that transition. They feel like they should be executed as different exercises. Yeah. Okay. Sorry, that's all I wanted to ask. A very extended, long question that probably.
Yes,
okay, Albert.
Maybe just a quick question, something a bit more basic. I think I remember when we talk about syntax and this generative form. I mean, one of this thing about discrete and continuous, right? I think maybe can we also explain a bit more to the students about like this differences between discrete formation and also continuous formation, because I think that's something that that will be quite crucial for them to understand the concept in this part of the parametricism.
Okay, let me go back. Something like this kind of, right? So basically it started with all this, they use Maya. Maya is a software to model for anime, right? For cartoons, right? So it's for human modeling, right? So you have all these kind of smooth surfaces, right? And then, or if you want a physical material, it'll be things like that, whether a lump of clay or like concrete and fabric, right? So you can't actually build this when you want to make this into a building, right? You can't take a bigger piece of cloth and then just drape. So you have to change them into kind of like discrete buildable modules, so-called. You see? So this whole era, they are basically struggling with that, how to do that, you see? They are not even thinking about like, oh, my structure is not parametric. I don't care. This is part of the the evolution, right? So they are just thinking about how do I have when I conceptualize my building, I'm no longer taking a block of wood and carving, or I'm not putting planes, points, things like that together, right? But I want this crazy form. I want a crazy form. But then how to build it, you see? So every time you build, you still go back to discrete or rigid material. Right? So I have I don't know, okay, there's this like this student also, right? So this past year project, can you all see?
Yeah, can.
Yep. Can.
Right, so these are like the common ways that you start with all this kind of material or this kind of material, right? How to make it into a building, right? So if you then he start to put into Rhino, and then you can see that the way this is he models this thing, right? Without this one, you still have a kind of pushback from the material itself. That means the cloth and all this can only be stretched or fold a certain way, right? But in Rhino, you see he struggled. This is completely not the process of that, right? Then until he understood, and then but before that, actually, these are all form and deform based on sound mapping, and how I can tweak this surface to generate different sounds for the space itself. Okay, so these are like the very specific series of experiments that he did. So this is assuming water wave behaves like sound wave. Okay, so then when it's like that, you lose all the precision and things like that, right? And then you go into this modeling, and then finally, this way, right? When you describe it using contour, the waffle system, then you can be very precise, and you can morph, and you can control like exactly the curvature and things like that you want. So this is discrete. So when you want to build it, it's always going to go into discrete. But in the beginning, you see, it's like that lah. So this is roughly only, but now with Rhino and all this, we can be very specific already. So so for me, exercise 4, right, is learning how to make this, and then you go into some sort of data mapping to justify your twist and turn, and then being able to model it in Rhino very precisely, right? And then after that, build it out of a discrete material.
I think that there's also a bit of confusion with not confusion, there are different ways to use the terms continuous and discontinuous, right, which is discrete. So continuous also means that we think about it topologically, that, if it's a piece of neoprene or a piece of cloth, or we think about a topology, whenever you do something to one end of this topology, it's not like the rest of the areas are unaffected. Discrete is, of course, there's another school of thought, which is not school of thought, another trajectory around this, which is prefabrication, right? So I can take a very complex form and I can pixelate it. But if I pull out one unit of a prefabricated housing unit, the other units are not affected. But it can prescribe a complex form still, because that is the way that is more buildable today, I suppose. You cannot just take out, in this model that Sai is showing, if I take out 4 ribs, it's very unlikely that the rest of the form is before it gets into this stage, when it's still a cloth or when it's still something that is responsive, it is still considered continuous. But once you discretize it into ribs, then you can build it. So discretizing it makes it, I want to say, a bit more buildable. And therefore, discretizing through the process of prefabrication and pixelation has a stronger following today only because it's more buildable. I think that for me, the primary differentiation in definition is continuous has to be a topological construct. Discrete is, you imagine you take out 1 straw, 2 straw, 3 straws, 1 rib, things are unaffected, right? Yeah, so that is my kind of baseline simple definition. Not to say that both cannot converge at the end to describe complex forms, they can still, but the responsiveness and the thinking about it as a field condition is more for me, more authentic if you think about it topologically.
Yep.
Thanks.
Thank you. Thanks. Okay, if there are no more questions and tutors are just talking amongst themselves, then we can go back to the studio.